Important challenges in the global water situation, primarily caused by global population growth and climate change, necessitate novel, innovative water technologies to ensure a supply of drinking water while reducing global water pollution. Against this backdrop, the application of cutting-edge nanotechnology to traditional process engineering opens up new avenues for technological advancements in advanced water and wastewater technology processes. An overview of recent advances in nanotechnologies for water and wastewater treatment processes, including nano-based materials such as nanoabsorbents, nanometals, nanomembranes, and photocatalysts, is provided here. Welcome to the Theory of Science. Do you wish to learn something new? Nothing is ever too late. Just hit the subscribe button. Constant population growth, which is expected to nearly double from 3.4 billion in 2009 to 6.3 billion in 2050, is accompanied by a 70% increase in agricultural production by 2050. Thus, demand for fresh water is increasing dramatically, particularly for food production, because agricultural irrigation already accounts for 70% of global freshwater withdrawals. Currently, 64 billion cubic meters of fresh water are consumed annually. Water scarcity affects the arid regions of North Africa and nearly half of the European countries. Even industrialized countries such as the United States, which provide highly innovative water-saving and purification technologies, demonstrate the difficulty of exhausting water reservoirs because more water is extracted than refilled. Micropollutants, for example, are entering water bodies at an increasing rate in both industrialized and developing nations. Traditional decontamination methods like chlorination and ozonation use a lot of chemical agents and, in addition, may result in toxic byproducts. Innovation and technology must play a larger role in meeting the challenges in a world where resources are becoming increasingly scarce. Advanced water and wastewater technology processes can now be developed thanks to the integration of highly advanced nanotechnology with conventional process engineering. In nanoscience and nanotechnology, matter at extremely small scales is studied and worked with. A single human hair is about 80,000 nanometers wide, or 1/1,000,000th of a millimeter in size. Carpet nanotubes and alumina fibers are two microscopic components used in nanotechnology-based water filtration. It also uses nanocatalysts, magnetic nanoparticles, and non-porous zeolite filtration membranes. Nanosensors based on palladium nanoparticles or titanium oxide nanowires are used to analyze containment and water samples. Future cities' vital water resources face risks that must be taken into account thanks to nanotechnology, which manipulates matter at the atomic level to produce materials with distinctive qualities and abilities. Nanotechnology has the potential to be a key element in the supply of potable water for human consumption, as well as clean water for agriculture and industrial uses. Today, scientists can design and produce nanomaterials to benefit from particular properties not found in their bulk counterparts. For instance, some nanomaterials such as nanometal oxides and nanofibers have large surface areas that increase their ability to absorb contaminants. Numerous nanotechnology-based water treatment products are already available on the market, and more are either about to hit the shelves or in the development stage. The technical problem of removing salt from water can be resolved using nanotechnology. Nanofiltration membranes are already widely used to treat wastewater, soften water, and remove dissolved salts and micropollutants. By capturing particles and microorganisms larger than their pores and rejecting certain substances, the membranes function as a physical barrier. For more videos like this, subscribe to our channel. So, can nanotechnologies really aid in the resolution of developing nations' water problems? Two encouraging indicators suggest that they will. First, local communities are becoming more involved in discussions with water experts and scientists to understand better the challenges and opportunities of using nanotechnology to improve water quality. Second, given that commercialization of nanotechnology is still in its early stages, we can only hope that these discussions between researchers, communities, and industry will motivate innovators to create viable business plans to capitalize on their discoveries. The majority of the world's water is saltwater, and even though technologies have been around for a while, desalination is a very energy-intensive process that requires expensive infrastructure. Reverse osmosis is the traditional method, which involves applying extremely high pressure to a semi-permeable membrane to force saline and polluted waters through its pores. Under pressure, these pores allow water molecules to pass through, but salt ions and other impurities cannot, leaving behind highly purified water. Nanotechnology is anticipated to advance membrane technology even further and reduce the impossibly high cost of desalination, the process of creating fresh water from salty water. Nanotechnology can detect waterborne contaminants in addition to treating water, to create small, portable, and highly accurate sensors that can detect individual chemical and biochemical substances in water. Researchers are currently developing new sensor technologies that combine micro and nano fabrication. Such devices are being field tested by several research consortiums, and some anticipate commercialization soon. The use of nanowires on a silicon chip, for instance, has been developed by a team at Pennsylvania State University in the United States as a method of detecting arsenic in water. Nanotechnology-based water filtration makes use of microscopic components like carbon nanotubes and aluminum fibers. Additionally, it makes use of nanoporous zeolite filtration membranes, nanocatalysts, and magnetic nanoparticles. For the analytical detection of contaminants in water samples, nanosensors based on palladium nanoparticles or titanium oxide nanowires are used. The impurities that nanotechnologies can address depending on the stage of water purification to which the technologies is applied. It can be used to get rid of pathogens, bacteria, charged particles, and chemical effluents. They clarify that by using nanotechnology, toxic trace elements like arsenic and viscous liquid impurities like oil can also be eliminated. The researchers note that the general public and activist groups have expressed concern about a number of fundamental aspects of nanotechnology. Since nanoparticles have a much higher surface area to volume ratio than bulk materials, they may be more reactive and result in interactions with biological surfaces that have not yet been recognized or tested. They admit that the risks associated with nanomaterials may not be the same as risks associated with the bulk versions of the same materials. Nanotechnology-based water purification hasn't yet caused any issues with human health or the environment, but the team agrees with others that more study is needed to understand how nanoparticles interact with living things. Thanks for watching! Don't forget to hit the like button and subscribe to our channel for more interesting content.